we're shifting gears slightly, and we will focus more on the biodiversity. And our next speaker is Markus Reichstein. Markus is a director at the Max Planck Institute for Biogeochemistry, and he's also a professor at the University of Jena. And his research interests are really how climate variability affects ecosystems and how this responds also to climate change. So today, Markus will pick up this topic with a talk called Breathing Nature, and he will unveil the biosphere's secrets through AI and Earth observations. Over to you, Markus.
Hello, yes, I would like to welcome you to this talk where I want to tell you what breathing nature is and why it's important for sustainable development goals and what science and AI can do to better understand it. First of all, let me start with a slide that you all know, or with knowledge that you all know. Climate is changing, it's happening now, and we are realizing, experiencing the effects of climate change almost every day somewhere on Earth. It is these impacts that matter, and these impacts are actually mostly not directly related to temperature directly, but to the water cycle, to too much water, too less water, droughts, and they emerge through domino effects and cascading effects, which I will try to explain to you in the next slide. Let's look at a heat wave as an example. Such a heat wave has hit Canada recently, India, Australia, Europe. And in 2010, there was kind of a prototypical heat wave in Western Russia, which is pretty well studied. So there's a blocking high system, nice weather in principle, blue sky, but no rain, on top of climate change, which then leads to a heat wave and drought, stressing the ecosystems. They are desiccating. This makes them fire prone. So there's a lot of forest fires that are developing from that, which affect the air chemistry with pollution, with fine particles, with nitrous oxides. And it's very important to note that then only this kind of indirect effect of the air pollution together with the heat wave actually put the strain on the health systems and mortality of more than 10,000 people. This was the case in 2010, but we have similar results, for example, for California, heat wave and fires, and so on. And then if such an event happens in a breadbasket, then the crop failure that is inevitable will then also lead to socioeconomic repercussions like high volatility in wheat prices. And studies have really clearly shown that this kind of economic volatility then causes, but at least adds to the causes of social unrest, something that we now know as the Arab Spring. So what's really important that if you talk about that and think about that, that the different sustainable development goals are actually connected, and we should not look at them each one after the other, but together. And climate change is not the only issue, but it's an important triggering issue. So we need to have a systemic view. We had experienced something similar in Germany, where we had these devastating floods in Western Germany, in Rhineland, where more than 100 people died, economic damages of more than 10 billion euro, triggered by a weather event, by very strong downpours of rain. But what less people know is that a very similar weather event happened a couple of months before in Mecklenburg-Pomerania in eastern Germany, and almost nothing happened. So we have the same weather, but different impact. Why is that? The landscapes look very different. We have loamy soils, dense soils, hilly terrain in western Germany in that area, and very gentle terrain and sandy soils in eastern Germany in that area. And so they do something very different with the same weather. In eastern Germany, basically the sand could be refilled with the water, which was actually good for the groundwater, while we had these devastating floods in Western Germany. So it's really important how ecosystems look like, how landscapes look like, and we need to model that. We need to have a system view on climate impacts. We need to integrate atmosphere, biosphere, and anthroposphere, look at the interactions, look also at the feedbacks, And it's very difficult to model that from first principles, how we can do it with weather. So that's why data is very important, that we exploit the data to understand those relationships that we cannot just describe with physical laws. So fortunately, we do have a lot of data. For example, from space, from remote sensing here, this beautiful image of Lake Geneva, where we are very close to, where you can see the eddies, the currents, and also the complex landscape around. We can also look actually deeper with radar remote sensing, where we can interrogate the vegetation and get a kind of tomographic scan and get the 3D structure globally of vegetation, so get even a better insight. These remote sensing observations also provide temporal information. For example, here from the ESA's Sentinel-3 in 2018, from green to brown in 1 month, basically showing how the vegetation responds to such a drought and heat wave as we experienced in 2018. Or longer time scales, thanks to the legacy of Landsat, we can basically observe what we humans are doing to vegetation here, the deforestation of forests in Madagascar, just as one example. But with this remote sensing observation, we don't really see the breathing of the biosphere. We don't see what ecosystems really do. We only see how they look like, but we don't see what they do. And ecosystems do a lot. It's called ecosystem services or nature contributions to people. Many are mentioned here. Many of them are related to climate, like related to carbon uptake, related to cooling the environment. Others are related, very important, to water purity and to food, to timber production. And it's hard to estimate really the value, but more and more studies do that and end up with values that are in the range of 100 to 200 trillion US dollars annual value that they generate, which is more than the global GDP. So we really need to understand what the ecosystems do. How can we do that? Our point is that we need to look closer. We need to do it like in an intensive care station that you can see here, where the pulse is measured, the respiration, the blood oxygen content, where basically 3 parameters are monitored continuously and 30 parameters every second day. So we need to do that for the ecosystems. And we have been doing that and continue to do that by putting a sensor on top of the ecosystems that measure the CO2, water, and heat exchange between ecosystems and the atmosphere, looking what the ecosystems are doing. We're using the turbulent flow in the atmosphere to do that. And we can generate every half hour over decades now estimates of what the ecosystems are doing here, how much carbon dioxide are they actually taking up. Here plotted as a so-called fingerprint of the ecosystem. X-axis is time of the day and then time of the year, as you can see. And we see, for example, a tropical rainforest taking up carbon during lunchtime every single day in the year, while, for example, European beech forest is dormant in winter, doesn't do much, and so on and so forth. So we have this information for many, many stations because it has been such a successful and appealing method. This network has been growing. It still needs to grow, for example, in Africa. And it still, of course, doesn't cover the whole globe. We have maybe 1,000 towers covering 1,000 square kilometers. That is not 1 million or 100 million square kilometers, which the air surface is. So we need to somehow go from these observations, what the ecosystems do, to the global scale, what they are doing. And for that, we need to build AI-powered models. We basically use the drivers, the meteorological conditions, and try to build machine learning-based models, neural networks, for example, that predict what the ecosystems are doing given the weather and other conditions. And then we need to compare that with the real observations to improve the model, and that is basically exactly the machine learning approach. And then we apply those drivers, these statistical predictors, apply that model globally with all the observations that we have globally, and we can come up with a global picture of what the ecosystems are doing. Here we see diurnal activity. We see how basically the sun moves through and the ecosystems can do photosynthesis, and we can do that basically every day. I should add one thing. We should, from a scientific point of view, amend the AI method and the machine learning method with still our scientific knowledge, with causality, with physical laws, bring that together in a hybrid modeling approach so that we get more consistent and robust predictions and can also predict unobserved variables. If we do that all together, we can get actually a mostly data-driven picture of breathing nature here, the CO2 uptake and release by ecosystems. It's an uptake if it's green and going in. We call it also carbon sink, and a release when it's more reddish. So this is a first data-driven AI-based estimate. We can, since the method measures not only carbon dioxide but also water, we can get actually a very holistic picture of what's going on. For example, how the water is moving up and down, north and south across the globe, how much heat is injected from the ecosystem into the atmosphere, contributing to heat waves. And we can link that also to the atmosphere and basically describe how the CO2 concentrations in the atmosphere change and how it's influenced actually by the ecosystems, and also how the groundwater resources change over time. And if we put that all together, also with other data, then we can also understand where is the system getting weird, where it's getting anomalous. So we can detect extreme events. We use these data cubes, many different variables that are in space and time organized, and we ask basically, where are the constellations of those variables strange? And with AI methods, then we can basically find these spots that are here indicated in this space and time on the right-hand side when the ecosystems do something very strange, or when the overall Earth system is strange, regionally very strange. And in this case, we detect, for instance, these kind of blob that you see here, and this is just derived from the observations that we have, the Russian heat wave, with all the consequences that I had mentioned before. But the challenge is, of course, also to go deeper, because this is kind of quite on a large and continental scale, and we do have deep observations, more precise observations with 10-meter resolution, where you can watch your own backyard. For example, here, fire development on the left-hand side, or the drying of a lake on the right-hand side, but it's actually currently happening. So we ask basically, are landscapes predictable from AI, with AI from climate? Geographers would say, yes, it should be possible. Climate, human, and geofactors cause landscapes. But I'm not aware of any physical model that can actually predict that, because it's just too complex. So we thought, let's adopt a method that has been developed in machine learning, that has been used also in the fashion industry to create photorealistic images, for example, of handbags here. And instead of having the input to output mapping that is shown here, we have an input to output mapping where climate and other geofactors are mapped onto landscapes as they are seen from space, with, for example, from those satellites that I just showed. And it works actually very well. So you probably cannot say which of these images are AI generated and which of them are really observed. I also forgot it, but okay, here it is. The upper one is the predicted one, the lower one, the observed. And the next challenge is basically not only to predict static landscapes based on average climate, but to understand how landscapes evolve over time, given a drought, given another extreme event. And this is work in progress. So this challenge to predict dynamically evolving landscapes from climate. Here an example from Greece. You see here this part of the landscape where we have a north-facing and south-facing slope, and here just an experiment what the AI method says with different climate inputs. So on the bottom it's hotter, and on the right hand it's wetter. How that actually affects the development of the landscape over a growing season. And you see it clearly, the large-scale climate effects, but we see also fine-scale effects, like north-facing slopes still stay green for a longer time, or the ridges, you see the ridges on top are red, they are desiccating very quickly, and so the vegetation browns first. And this is very important for local prediction of climate effects and for early warning. And we really believe we need to adapt to climate change. We need to mitigate, but we also need to adapt. And AI can help with adaptation by embracing the whole early warning chain, from observation and weather forecast to hazard and the impact forecast, but also for the warning, for the communication itself, and for the decision making. So we have basically prediction task for AI and information or communication task. And just a few examples, of course, weather forecast is a very essential one, and we have seen a lot of breakthroughs in the last years on that. We need to predict what are the impacts. For example, here, can we really say which areas are inundated so we know who is endangered, who is vulnerable, who is not? And then we can even go with generative AI and generate images of properties so that people can more intuitively understand if they are endangered by a certain climate extreme or not, instead of having these abstract numbers, 200 millimeters of rain or 8 meters of water or something. This will probably lead to a better response to those disasters. So let me end with this one. We have a complex system. We need to understand it. The breathing biosphere plays a very important role in this whole Earth system. And AI will do the best job if it connects to the different sciences so that we can have a better understanding what's going on Earth. I would like to acknowledge quickly the Max Planck Society for funding the research, also the Alice Network, and the European research funding is also very, very fundamental for what we are doing. We are really grateful that we are living here and have such a good support for science in Europe. And if you want more info, there's a lot of information, the Max Planck Forschung, Max Planck Research, both in English and German, and write an email or text me if you want. Thank you.